learned. For that case, as we said, this is 1D strain stress path, and this is different than a triaxial stress path. All right. How do we know what is the signature of the rock, the actual relationship between? Forget a minute about this. This normal compaction trend. How do we know that? We could either use, as done in this problem, use just this part of the data and use that to define this relationship, or we could also do experiments in the laboratory. It's the same thing. Probably if you do a combination of both, that would be much better. So I could run these experiments similar to these experiments in the laboratory. And that's what those are called a consolidation test. Okay? In that consolidation test, very similar to this, I'm going to get a piece of material of sediment that usually it's a sample which is much shorter than the diameter, about half of that. I'm going to put that into a vessel. This is a cylindrical sample most times, and it has very thick walls. So as I apply stress, the sediment does not deform to the sides. You apply stress by putting a end cap on the top and the bottom. Most times these sediments are fully saturated with the fluid, right? And many times water. So if I were to apply an effective stress in this direction, what should I do if the sediment is filled with water? I mean, if I compress it, and I'm going to tell you a little bit more. I'm going to put an O-ring over here so that the fluids cannot escape in between the walls of the steel vessel. So if I don't let the fluid escape, that's not going to compact. I'm going to measure the undrained constraint modulus of that, and that's not what I want to measure. I want to measure compaction as a function of stress, or porosity as a function of stress. So in order to do that, what you do is you make a hole over here, and you let that fluid escape as you run this test. Most times too, in order to run this a little bit faster, you want to make a hole on the other side too. So the drainage length is shorter. So I'm going to make a hole on this side too. Of course, I want to make sure that I have a reaction on this side, so the water can come out of that. And in addition to that, many times here you will put what is called a porous plate or a porous stone, so that fluids that, let's say, are over here, they have the same path to a low pressure condition if either they are here or they are right close to that pipe. Okay, so this is exactly the same as that one, but now in the laboratory. If you were to run such tests, usually what you would do is you would apply loads with time. And as you apply loads with time, what you do is you measure what is your porosity. Wait a minute. I have inversed the axis. I have it wrong in my notes here. This is porosity, and this is sigma v. So what you would expect to see, it's this compaction trend, which, as we said, is going to be what? Non-linear, right? So it's going to be a curve. If you do loading, say that we start here, okay? We start here, we can do loading up to this point. If I do unloading, it's not going to come back through the same path because we have plastic deformation. I'm assuming that I'm going over the yield surface. So this is going to come back in this direction. If I do reloading, though, that's going to be elastic. And the unloading is also elastic. If I do reloading, I come back to that point and I continue loading. I can do another reloading, unloading here, reloading, and whenever I pick up the compaction trend, I'm going to come back to that line. So this is going to be the normal compaction trend of this material. A very important concept here is what is called pre-consolidation stress. That is the stress that if after I do an unloading, I need to reach in order to come back to the normal compaction trend. So this line is the normal compaction trend or virgin compaction trend that before you get into there, you do an elastic recompaction and then you get into the plastic part. There is an easier way to take a look at these plots. How are we doing with time? Over time. Let me just finish this. Instead of computing or plotting porosity as a function of vertical stress, you can plot this as a function of the logarithm of effective stress. And now this is just going to look as a straight line. If you have unloading, it's going to be straight line 2. And if you have another unloading over here, it's going to be straight line 2. But it's much easier to see than with this nonlinear plot. All right, guys, start working on the project. You see, it's not a lot of work. You can already solve problem number 1. And then we need to finish this discussion in order for you to solve problem number 2. Okay? Have a great weekend. I'll see you on Tuesday.